yeah, like, you just hit that. Anyway, I want to talk to you about the homework calendar stuff first. Talk a little bit about logistics for the next week, and then we'll jump in and do some new content. Does that sound okay?
Yeah.
What's what?
The Dark Matter video.
We got as far as we wanted to get. We'll talk a little bit about it in just a second. Hold on. Okay, so to be very, very clear, I got a couple of emails a couple days ago saying, "Oh my gosh, do we have to have homework done?" Da-da-da. No, I'm not going to stamp homework today. Okay. So if you did homework, good for you. You don't have to worry about that homework for next time. Okay. I'm going to go ahead and write down all of the homework for Chapter 8 up on the board so that you can write it down as well. So this would be fill in your chart, and I'll also put down due dates so you know when things are going to be due. So this is all Chapter 8 homework. Okay? On Monday. So I'm going to say due Monday are numbers 2, 7, 9, and 11. And I've already told you those numbers, right?
Yes.
You had those written down. But I'm just making really clear when things are going to be due. On Wednesday, numbers 14, 18, 20, and 21. I thought I did. I think the next ones are new. I think.
Yeah.
We'll find out. They are? Okay, sweet. On Friday, numbers 24, 25, 27, and 29. And then the following Tuesday, 31, 33, 34, and 37. Does that make sense to everybody? So these are the days that they will be checked in, that they will be stamped, okay? A reminder that that Thursday is the last day I'll see you before winter break, and we will have a test over chapters 7 and 8 on that day, okay? Questions so far yet? Yeah?
What's the can rolling competition?
I will tell you about that if we decide to do it. That was kind of a brainstorm in my brain that I'm not sure I'll let you know.
Where else would a brainstorm
Can
be?
we do it?
I don't know, in your ear or something?
Can?
Were you were just trying to say a pun, weren't you?
No, that was like coincidental.
Oh, okay. I hope to if we can get there. Does that make sense? So because I'm going to be gone some next week, I'm just not. I don't want to do something for the sake of doing it. I want to do it because it makes sense, like in the context of what we're doing. Does that make sense?
Yeah.
So I'll let you know for sure next week, at the end of next week, what we're doing. Is that fair? Okay. So today we're going to talk about torque. We're going to fill in any last minute questions about chapter 7 that you need and start working on some problems just so that you're aware of what's going to happen on Monday in class. You're going to work on a problem set. More practice. And then on Wednesday of next week, and this doesn't quite match what your calendar says, that's why I'm telling you this. On Wednesday, you'll do a lab about torque. And you'll understand what torque is by then, so it'll be okay. All right? Friday, I'll be back. We'll fill in pieces as they need to happen, and we will torque. That's the word. Okay, it's not the word you're thinking, it's torque. Okay, I want to make that clear. We're done with that joke. Everybody good? Sweet. All right, if you missed out, too bad for you. All right, on Friday, we'll start talking about rotational kinetic energy and rotational momentum. Okay, does that make sense to everybody? Everybody's happy? Yes?
On the black holes and dark matter, like homework spot, it says handout.
Yeah, I changed my mind.
Okay.
Don't worry about it. I want you to, I hope that was kind of a interesting, thought-provoking, kind of weird thing, but it's not, there's not going to be homework with it. I had something, yeah. Again, it was a brainstorm that, that's just that's how things work. You know this, yeah. Gemma, did you have a question?
No.
Okay. All right, so I'm ready to jump into chapter 8, but I realized that we didn't get to talk about homework questions from chapter 7. So what I want you to do right now, I'm going to give you like, I don't know, a minute to wiggle around. If you need to get a textbook, get a textbook. Pull out your homework from chapter 7. If you have questions, I would like to go over that right now, okay? So I'll give you a minute to get where you need to go, and then we'll discuss. Yeah, hold on just a second. Let me get a stamper. Was there anybody else? Amanda, you need stamps too, don't you? There you go. Thank you. You're welcome. There you go. Did I miss anybody else for stamps? Lizzie. Thanks. And so that everybody knows, I did post that last class up on YouTube, so if you just need to, so for those of you guys that were gone, we had a really good conversation, so I would strongly encourage you to watch it. And if you just want to relive the wonderfulness that was the last time we were together, you can do it forever, anytime you want. What's up?
Do you have like YouTube thing? Sarah last time how you were using to find it.
I don't know it off the top of my head, but if you send me an email, I'll just send you the link. How about that? Is that fair? Yeah, yeah. And there is a link on Infinite Campus. Like if you go through into the newsletter thing, you can get it there too. Okay. All right. Homework questions from chapter 7. Are there any? Let's go. Okay, so hold on. Let me move down here. All right. So I'm just going to grab numbers and then we'll go through them. Go.
38.
38. Bunch of hands went down. Yeah.
40.
40. Go here.
35.
35. Others? We happy? So everybody open your books. Oh, what? It's okay. All right, open your books so that you're all looking at this. I want to look at it too. One more. What?
31.
You say with confidence. Is that really, yeah, that's the one you really wanted? Okay. All right, so I'm on page, I don't know, like 270-ish. Let's just go in numerical order. So we're going to start with number 14. So I guess it's on page 269. Correct the following statement. The race car rounds the turn at a constant velocity of blah, blah. What's wrong with that statement? Miss Mara.
Only the speed is constant, not the direction.
Yes, only the speed is constant, not the direction. Is that okay? Velocity is a vector. Yes. We good with that? Everybody happy? Okay. All right. Next, 31. 31, comment on the statement. Oh, comment on the statement there is no gravity in outer space. We get this now, I think, maybe. Is there gravity in outer space? Yes, I mean, based on that, yeah, probably. Yes, so talk to me about it. Go, yeah.
In order for planets to orbit the sun, gravity has something to do with it.
Yeah, it has to be, right? That's how the planets orbit the sun. Let's take it bigger. Maybe gravity only exists in our solar system. Is that the case? No, how do you know that's not true?
Black holes have gravity.
Black holes have a gravitational pull on everything around them, right? On the video that we watched last time, they were talking about the Andromeda Galaxy. Do you remember? Yes? And they were talking about Triangulum, that other galaxy. So there's a poster of Andromeda up over here. I don't know if you've noticed it before, but it's there. It's been there forever. The Andromeda Galaxy has a black hole at the middle. You're like, but it doesn't look black. It's because there are a lot of stars all around it. Okay? All of those stars are being held in orbit by what? Is it strings? Are there strings attached? No, it's by what? Gravity. So let me ask a question. How many of you have seen some movie that takes place in space? It can be anything, any movie. Apollo 13 even, or like really? Never? Wall-E, yes. I mean, animated will take. Have you seen Wall-E? She's like, yes. Okay. All right, so you can put your hands down. In those movies, they depict people, and I want to be really clear, I'm not trying to break any of your hearts or your minds or anything. They didn't actually film them in space. Okay, that's the first thing I need to say. Second thing, I know, I'm sorry, Katie. Everything just collapsed. I apologize. They didn't take place in space. it looks like there's no what when they're like moving around inside the space capsule or the whatever. There's no gravity, right? You have these people floating around. How does that work? What's going on there? That's a little weird and messed up because you just told me that there's gravity in space, right? So you're lying to me? I'm sorry. Go.
There is gravity in space, but it's not pulling on them like strong enough for them to be like able to stand on the ground like we would because we're on Earth. But they're still being pulled by gravity.
Okay. Sam?
They're free falling around the Earth at the same rate that the spaceship is. So.
High five for that. Oh, come on. It's an air high five. Come on now. Humor me. Thank you. Yes. Did you guys all hear what he said, or did you need to say it really loud again? Loud! One more time.
They're free falling around the Earth at the same rate that their spaceship is. So they're like, it looks like they're floating.
Yeah, yeah. So the reason that it looks like we're standing on the ground is because the ground is right there, right? The ground isn't moving. Well, it is actually, but in our reference frame, it's not moving. What happens if the ground is falling at 9.81 meters per second squared? Just like we're falling at 9.81 meters per second squared. We'd still be going, right? But we would kind of be like floating above it. Does that make sense? There wouldn't be a normal force pushing back up on us. Going back to chapter 4, does that make sense? There's no normal force pushing up on us. So yeah, that looks like we're floating. Do you remember the picture we drew last time with the little, oh, it was somewhere. It was such a cool picture. There it was, this guy, where we were launching stuff, right? So if instead of just, I was launching the frog, was I not?
Yeah.
Okay, instead of just launching the frog, what if I launched the frog in a little space capsule? Okay, so I've got this little it's kind of like it's a little sphere, and then the frog lives in it. If I'm just holding the frog in the space capsule, and the space capsule is pushing up on the frog, yes?
Yeah.
And gravity's pulling down on the frog, and so he's not accelerating. F net is 0, okay? But if those two things are both falling, then what?
Acceleration?
Equal accelerations, okay? So even though they're both accelerating, even though there is a net force on both of them, the capsule isn't pushing back on the frog, so it doesn't look like he's like stuck to it. Does that make sense? So is there gravity in space? Yes. When they do this, it's just that they're falling. Do you guys know how they do the videos or like how they, make these movies where they're floating? No, it's not.
Don't they like get in a plane or whatever and then they,
Yeah, they get in this plane. It's called the Vomit Comet. Okay? Why? Because if you've ever been in a plane, like it's never like a lovely experience, but if you have a plane, this is what happens literally. They go up, 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 like anybody does in any plane. And then, in order to be able to float, the plane has to be nearly at free fall, just like the people are, right? So it goes like this, okay? And they make the movie while they're going like this, and then they pull up again, and then they don't make a movie right there, like, I don't know, eating snacks or whatever, and then they go down again, and then they're filming. Do you know what I'm saying? They go, I'm kidding. I'm just kidding. I'm kidding. Jeez. Yes. So up and down and up and down. They only video during the downs because that's when there is no gravity. No, that's not true, right? But that's when it looks weightless. Yeah.
I think I've actually seen that.
The Vomit Comet?
Yeah, and it's like the front is like really big.
Yeah.
So that way there's like more space so that whenever they go down,
They've got a little
up.
Yeah. Did you see where did you see it? Do you remember?
It was a few years ago in Arizona. They have a plane.
The Air and Space.
Yeah.
I've been there. I love it. So cool. If you're ever in Phoenix, it's in Phoenix, right? In Tucson, we go there like, whenever we're in Arizona. It's so cool. Totally worth the afternoon. Anyway. Okay, Vomit Comet, write it down. It's good. You don't have to write it down for anything, but it's just cool. All right, did we answer that question sufficiently? Does anybody have any questions about that? There is gravity in space. That was the short answer. All right. Whew. 35. 35 says, oh, it's the same question, eh? Okay, so are we okay?
Yep.
Okay. See, that's why it took longer, because we're answering both questions. Yes, I planned that. 38. Tarzan. Oh, yes. We love Tarzan, don't we?
Yeah.
Tarzan's always a good problem. Tarzan tries to cross a river by swinging from one bank to another on a vine that's 10 meters long. His speed at the bottom of the swing, just as he clears the surface of the river, is 8 meters per second. He does not know that the vine has a braking strength. Ooh, that's too bad. What is the largest mass he can have? Okay, so we got to think about this a little bit. So here's the vine, and here is Tarzan. And at the bottom of his swing, don't judge. You can draw him however you want. This is how I draw Tarzan. At the bottom of his swing, is he feeling a force? A net force?
Yeah.
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 Is he always feeling a force? At the bottom of that swing, let's think about this. Let's say that instead of swinging, Tarzan just goes like this. Does he have a net force acting on him?
No.
No, right? How many forces are acting on him?
2.
2. What's acting?
Gravity.
Gravity and tension, they're equal, no acceleration. But when he goes like this, is he accelerating through the bottom there?
Yeah.
He's accelerating through the bottom, which means that there must be a
Not force.
net force. Does the force of gravity change?
No.
No, because the force of gravity is just as mass times the acceleration due to gravity, right? So that's not going to do anything. So that means that the tension must change. If you've ever, like, I don't know, swung anything in a circle, you notice that the faster you go, the tighter the rope feels. Have you ever felt that?
Yes.
Ever felt that kind of feeling? It's because that tension has to cause that centripetal acceleration. Are you with me there? Does that make sense? So if we're just going to look at this like it's just a net forces problem. So you've got Fg pulling down, you've got Ft pulling up, and you're going to say F net. I mean, this is exactly like the ones that we did in chapter 4. So Fg goes down, Ft goes up. Is he accelerating now, though?
No.
As he goes around in that circle?
Yeah.
Yeah, he is. Yeah, he is. Because his direction is changing. Is it okay if I write it like that?
Yeah.
Okay. Can you find Fg?
Yeah.
Mass times 9.81. We know the velocity. It says velocity, right? It tells us the velocity. It tells us the radius. What's the radius in this case? The 10. We know that the maximum tension force is given. That's the 1,000. That's as much as it can pull. The smaller Tarzan is, the smaller the tension force is going to have to be. Okay? The bigger Tarzan is, the bigger the tension force is going to have to be. We want to know what M is. Do you want me to give you a minute to give that a shot? Okay, go ahead. It is definitely okay to talk to each other. Get you to be doing well. Does that sound okay? Mm-hmm. All right, let's go through this. So this is like mg plus, I'm gonna make that negative so I don't have to worry about my negative sign later. Is that okay? So that's gonna be negative because it's going the downward direction. This is ft. This is mv squared over r. What are we trying to solve for? M. Let's get them together. Help me out, algebra friends. What can I do to get those m's together? First step, go.
Add m to the other side. So add mg to both sides.
Okay, that sounds good. Okay, so I'm going to have ft is equal to mv squared over r plus mg. Is everybody okay with what just happened there? Yes. She is, but she's the one that told me to do it. So is everybody else okay with what happened there? Yes? Okay. Somebody else, what's the next step? What could I do next to kind of get myself in the right direction?
Like factor m of those things used to m times v squared over r plus g.
M times, is this what you mean? V squared over r plus g. Are we okay now?
Yep.
Now what, friends? Somebody else. Ooh. I want to get M all by itself. Go.
Divide by the quantity v squared over r plus g.
Yeah, the really nasty stuff, right? Yeah, so we're going to have something like ft divided by ugliness. No offense to it. I'm not trying to upset it, but something like that. Yeah. And then you just got to plug it in. Are we all right? Aaron, you feeling better? Okay. Okay, good. This G is going to be positive, just for clarity, just to make sure everybody's okay. Thinking is still happening. We doing all right? Okay, I'm going to give you just another moment to plug it in, make sure that we have found success. The answer should be something like, I don't know, 62. Again, making sure that this is positive 9.81. Are we okay to move on? Do you need another moment? Talk to me. The only feedback I'm getting is saying move on. Yes, move on? Anybody want me to wait? Wait! Okay. Okay. I'm going to keep going because we've got lots to do today, so I don't want to waste time if we don't need to. I'm going to take a look at number 40 here really quickly. 40 says, if the gravitational force between the electron and the proton in a hydrogen atom is this, how far apart are the two particles? So, it may have been that when you read number 40, you just freaked out because you're like, electron, proton, what? That's scary. Or maybe you looked at the numbers and they were like really, really small and you're like, oh my gosh, that's scary. You don't need to be scared though. Let me show you why this doesn't need to be a scary experience for you. Do you know how to find the gravitational force between two massive objects?
Yeah.
Yeah? Yeah? How do you do it, Victor? What equation do you use? Do you remember? It's like, I know it's in my notes.
I hope it's in my notes.
Me too. And it does also appear on your equation sheet, just so that you're aware. On your
Is it the big G times M1 times M2 divided by R squared?
Love it. Is that okay with everybody? In the problem, they give you the mass of the electron. It's quite small. They give you the mass of the proton. Also small, not quite as small. They give you the force. You know big G because it's a universal gravitational constant. Always the same thing. Can you solve for R? That's all they're asking you to do. Is that okay? Okay. So that's what needs to happen on that one. Does anybody have any questions about that? Looks like you have a question, Becca.
No.
No? Okay, just a contemplative look for the moment. Okay. Yes?
Are we gonna go through this?
I wasn't planning on it unless you need to. I mean, you just need to solve for R. How do you get R all by itself?
Multiply both sides and square root.
Boom. Well, and then divide by FG. But I think you were thinking that in your head. Yes. Is that okay with everybody? I can go through it if you need me to, but I feel like we've done things like this, so. Are we okay? Okay. I want to totally transition to new stuff then, if that's all right. So, you can put those books away. Well, actually, just close them. We'll need them in a little bit. Close the books so they're not a distraction. Put your homework away. Brand new chapter, so new page, or at least new side. Like, let's start fresh. Okay? Here we go. Chapter 8. You ready? You can close those books in front of you just so that they're not like taking up so much space on your table. I'm going to start by telling you a story. It's a story about Hannah and Lizzie.
At least I'm not
I heard it was true. I don't know. The names may have been changed to protect the innocent, or maybe not. I don't know. Here's the story. Hannah was reorganizing her living room. And one of the things that she needed to do was to move a table. There was a big table. It looked, I don't know, something like this. And she needed to move it. And so she said, okay, well, it's at rest. I guess I need to apply a force to it to get it to accelerate so I can move it. Does that make sense?
Yeah.
That's what she said in her head, not just like, oh, I need to move the table. She's like thinking about physics, right? And so she hunkers down and she pushes on the table. And it doesn't move. And so she pushes a little harder. And it doesn't move. She's like, hey, Lizzie, get off the couch, stop watching those crazy cartoons and come over here and help me. So Lizzie comes over, and so Hannah's standing here, and Lizzie's standing here, and they both push on the table, and by golly, it moves. That's great, right?
Yeah.
So tell me what we know so far about this story. There's more to it, but that's the first part of the story. What do you know, Thunder?
Hannah is trying to move a table.
Yes.
And she can't do it by herself.
Yes, because she doesn't have enough
Force.
Okay.
But with Lizzie's combined force,
Yes.
they are able to move it.
Okay. Life is good? So the F net, the net force of the two of them added together, okay, allows the table to move. Okay? So part of the reason that she was having a hard time moving was because it was on this crazy bright green shag carpeting that Hannah's family has all over their living room. It's awesome. So anyway, they got it off of the carpeting and onto the wood floor, and so now they're pushing it and life is good, except they seem like they're friends most of the time, but you gotta watch out. Sometimes it gets a little ugly. I don't know who said what to whom, but I know that somehow they got in this little spat, and Lizzie's like, forget this, I'm not gonna help you. And instead of going to sit down because she's a little vengeful, watch out, okay? Hannah's still like, I've gotta get this table to move a little bit further. I'm gonna keep pushing because now what's changed between the carpet and the floor? Coefficient of friction. So now she could get it to move herself, right? Like she can handle that. Lizzie's like, psh, you're not moving this table. I don't know what their fight was about, but this is how it played out. And so Lizzie goes on the other side and she's pushing the table this way. So Hannah's pushing this way, Lizzie's pushing this way. Let's say, for story's sake, that they can push the same amount of force. Does that make sense? Okay, so Hannah's pushing like this, Lizzie's like, and what's going to happen to the table? It's not going to move. Why? Go.
The forces cancel out,
So the net force is 0, so the acceleration must be
0.
right? I want to make sure we're doing this in good physics ways. So now they're like they're making these really scary faces at one another, right? Okay. But then Hannah's like, I'm going to do something a little tricky. So instead of pushing here, she takes a little step this way. Lizzie wasn't paying attention, so she's still pushing this way. Hannah's now pushing over here. What happens? What happens to the table? Yeah. I can't hear you. Say what?
Part of the table will go
This way. And what happens to this part of the table? It
Doesn't
doesn't
move.
move?
Doesn't move as much.
Maybe not as much, but as a result, what's going to happen to the whole table? What does it do? Is it going to move? Is it going to go translationally, like towards the place that Hannah wanted it? Not really. What's going to happen to it? It's going to rotate, right? Are you with me there? Okay. So if we drew pictures of this, kind of like of the story, like a little flip book of this from looking at it from above. So here's the table. Here's Hannah. I'm just going to tell the part of the story once the fight happened, because really the other stuff was just, whatever. So here's Hannah, the force of Hannah. And here's the force of Lizzie. Is everybody okay with what's going on here?
Yeah.
Okay? And nothing happens, right? No movement, nothing, no acceleration, life is happy. Or not, depending on if you're one of the two of them, because they seem unhappy in this story. Same table. Lizzie's still pushing here. Hannah pushes here. What's the net force on the table? Let me back up. What was the net force here?
0.
0. So F net here is equal to 0. And as a result, we know that the acceleration is equal to 0. What's the net force here?
Well,
It has to be something because
so it's
yeah,
not 0.
it's not 0.
Something greater than 0.
When you say here, do you mean the entire table?
In this story,
Okay.
what's the net force acting on the table?
Something greater than 0.
It's not really
Something greater than 0.
On the entire table, it stays the same.
F net here is 0. F net here is,
Something greater than 0.
how do we find the net force, Tanner?
You add all the forces acting.
Add all the forces acting, right? We've got a negative and a positive. We've got a negative and a positive. The magnitudes haven't changed, so what's the net force?
0.
0. It's weird. That's causing some of you to be like, what? Because why?
It's moving.
It is moving, but is it moving in translational motion in this kind of like straight line motion?
No.
No. What was that O back there about?
Oh wait, no, because I read. Yeah, I
Huh?
remember this now.
Yeah. It's going to rotate, right? Rotational motion, translational motion, not the same. Are you with me here? That's a big deal. Let's write this down. This is humongo. So F net equals 0. The acceleration, this thing is talking about straight line motion. Is still 0. So the table itself is not going to like move in this direction. But you know from experience, maybe because you've had fights with this fights like this with somebody else, that this table is going to rotate. It's going to turn, right? So there's something that isn't 0. You with me there? There's something that isn't 0.
Rotational motion.
There's some sort of rotational something, right? So this thing is it's gonna rotate about like a spot right there. Does that kind of make sense? And it's what? Torque. Oh, it's torque. It's this new thing. It's this new thing called torque. So here's the funny part about torque. Torque is something that will cause, let me back up. Torque is marked with this letter. And that is not a letter that we are super familiar with, although you stare at it every day when you're in here. Do you all see the thing that looks like a capital T up there? Yeah, that's the letter tau, okay? It's the capital letter, the capital Greek letter tau. And then there's one right next to it, the little one. That's little tau. And that's what torque is marked with. Little tau. I make it a little curvier, otherwise it just looks like a T to me and then I get confused. So I make it with a little curvy top just so that I can keep track of this thing is not like time or something crazy like that, right? Like it's something different. So torque is marked with the letter tau, and the net torque, if the net torque is not 0, what do you think might happen? It'll move, but not just move, it will rotate, okay? So if the net torque is not 0, then the object or system will rotate. Does that sound kind of familiar? Like we've talked about something kind of similar before? Go, Asmara.
It's like when the net force is not equal to 0, then it's accelerating.
Same deal. Same thing. Do you see what I'm saying? Do you see what she's saying? Like this is, it's like this nice equivalency. So when the F net is 0, acceleration is 0. This translational, this straight line acceleration is 0. If F net isn't 0, then you know that the thing's accelerating, right? Same game here. If the net torque is not 0, the thing's going to rotate. If the net torque is 0, then what?
It won't rotate.
Won't rotate. Won't rotate. Okay? It's just Newton's first and second law again. All over again, just with something a little different. So, how does one increase torque? How does one increase the torque acting? You're like, I don't even really know what torque is, but I want you to try, like, from your gut. I'm going to tell you that the net torque here is not 0, right? Since that thing is is rotating. Gemma, you look like you wanted to say it.
Would you make one of the forces greater or both of them greater, and then it would turn more because there's more force acting?
Yep. So if you increase the force acting, that will increase the torque. There's another way to increase torque.
Wasn't there something about like changing the point where the force is applied?
Ah. Riley, what were you going to say?
I was gonna ask, if you increase the force, you have to increase the forces equal, right?
Well, not necessarily, because in this case that's a really interesting question. So it's kind of a two-part question given the setup that I just gave you, okay? So let me answer it in 2 pieces. That was a much deeper question than I think you meant to ask, but I want to make sure that I answer the whole thing. Okay? So, if we want this thing to just rotate and not move in this direction, then the net force has to be what? 0. Is that okay? But if we don't care about any like motion in this direction, then Hannah could just push really, really hard. And then it would like do this like thing.
Wait,
Huh?
can torque not equal 0 if the net force is not 0?
Say that one more time.
Can torque not be 0 if the net force isn't 0?
So if F net is not 0,
Is it possible for torque to not be 0?
Yeah.
yes and no. All of these good questions. So the yes and no part of that question is, if this thing is like, so like instead of it just having this place where it's going to rotate about, if it's like attached to something. So let's say I have this meter stick. Thank you. I was going to try and make it something more interesting about meter stick. And I drill a hole and I hold it here, right? Then different things can happen that way as opposed to if I just like let it fall while things are happening. So that's one of the pieces. The other thing is that all of the analysis and things that we have done when we're talking about things moving like frogs flying, okay, we have assumed that the frog is all one thing. It's all at one point. But, are you ready? Trying to catch this frog? Okay, actually, here, come here, stand over here so that people can see it. I want you to watch the frog. So you know that if I throw the frog, it's just going to be projectile motion, right?
Yeah.
Life is good. But I'm going to hold on to the frog from the foot. Now we're going to acknowledge the fact that the frog has lots of pieces. And if I throw him like this, not only is he doing projectile motion, but he was also doing what? He had some torque, so he had some rotational stuff going on as well. Thanks for catching the frog for me. Does that make sense a little bit? There's a lot to it. We'll get there. We'll kind of get it all put together. Okay. I want to come back. Who is talking to me? I don't remember. What did you say? What was your other piece?
Changing the point at which the force is applied.
Yeah. So let's say that Hannah, Lizzie, because Lizzie's getting all smart about this now. So Hannah steps over here. What if Lizzie steps over here? All right. It's going to be different. Do you agree? Yeah. So that's what we're changing there. So I'm going to say that if we increase, to me, I like to call that the radius. Increase the distance from where we're applying the force to where it's going to rotate about. Are you with me there? Okay. If we increase the radius, we also increase the torque. Okay. Let me give you a subtle, do you know what subtle means?
Yeah.
What does subtle mean? Have you guys heard the word subtle before?
Yes.
Yeah. Not obvious. A subtle change that has happened in public buildings in your lifetime. Okay? If you go to an old building, like an old house or something like that, and you look at the doorknob, what does it look like?
Round.
It's a round doorknob, right? And to you, you don't think about that much. You just grab on and turn, right? Like no big deal.
Yeah.
If you look at any, especially public buildings now, have you noticed what the doorknobs look like? Huh. It's like the hand, right? So either you've got that thing, but if you have one that you have to turn, right? Like the kinds that you have to turn. Do the doorknobs in this building, are they just round knobs anymore? No, what do they look like?
They're like a bar.
They're like a bar. So if we think about that, if we have to turn something and we can either apply a force, so this is like the old school ones, okay? We have to apply a force right here to turn this thing. And you don't really think about it, but it's the friction. I mean, like if we're really going to talk about it, right? It's the friction between your fingers and the doorknob that make you able to turn it, right? Like if you put lotion on your hands and then you try and turn an old doorknob, it makes it really hard, yes? Okay? Same kind of deal. But the new ones, here's the middle, like that's where you put the key. But then the doorknob is like this. Which means that instead of applying a force right here to try and get this thing to rotate, you can apply a force way out there. What does that mean?
You're increasing the radius.
You increase the radius, so even with just a little bit of force, you can get this thing to turn. You with me there? You can get this thing to turn with just a little bit of force, whereas if you were pulling right in here, if you had this kind of doorknob, you'd have to apply a whole lot more force. Okay? So here in these I'm gonna write this down, doorknobs, so that when you look at this again, you're not like, what is she drawing pictures of? Okay, so doorknobs. With the new ones, we increase the radius, and in doing so, we increase the torque given the same force. What's up?
Did they just change the doorknobs because now the ones are easier to turn, or was it like another health safety thing or something?
Well, so I mean, it all kind of, I mean, cause and effect, right? It's not like you were like, oh, I'm just going to invest in new doorknobs, right? Like, oh, everybody needs new doorknobs. No. It came from a law that was a piece of the Americans with Disabilities Act, right? So people like, especially like older people, right? Or people that just have, they're not able to apply as much force. They can certainly open this much more easily than you could something like that.
Okay.
So it all has to come from legislation somewhere, right? Yeah, because even though we want to believe that everybody's good and we'll just do things for good reasons, that doesn't always happen. Always, darn it. Okay. Let's talk about another example that might kind of give you perspective on this. Just opening a door. It's all about doors today, I guess. Actually, I have two more examples. They're both about doors, so have fun. All right. So let's talk about opening an actual door. So this is like looking above, looking at a door. So this is the doorway. That's the hinge. Okay? If you're going to push to open a door, so let's say the doorknob is open or it's unlocked or whatever, and you're going to push to open the door, where does it make the most sense to push on the door? Farthest from the hinge, right? Have you ever watched somebody who isn't familiar with the door and they start pushing right over here? And then, if you've ever done this, I don't know, I've done this before, and then you look around, is anybody watching me? I feel like I'm kind of crazy, right? Can you apply a force right there and open the door?
Yeah.
Yeah. Whoa, right, you gotta push like crazy monster. But you can push over here with almost no force. You with me there? Same thing. So we're getting this thing to rotate about the axis. Okay? It's a whole lot easier to do over here than it is over there. That's torque. Okay? You look like you're a little perplexed. Talk to me.
Oh, me?
No, Trayton.
Okay.
I don't know. For some reason, I thought you were talking about a revolving door.
We're getting there. We're not there yet. This is just like this plain old door here.
I was just looking at a doorknob, right? Then all of a sudden I saw it as an aerial view of a.
Yeah, that's what this is. So this is like
door.
looking above, but this is just a hinge.
Okay.
It's just a regular plain old door.
All right.
Is that
It was
okay?
the same as your doorknob.
I know, right? Yeah. You have to listen. That's why. I know you're
Zoned
listening.
out.
But I know, right? So there you go. So that's the door. Yeah. What's up?
So the farther the distance you are from the axis or whatever, the easier it is. Does that make the torque bigger?
Huh. Yeah. So let's write down the equation that goes with this because I think it'll help you. How about that? So, you know how sometimes I don't like the way things are written in the book. Have you noticed that?
Yeah.
In the few months that we've been together? So I'm going to tell you my way and then I'll put in parentheses what the book says. Does that sound okay? So I like to say, just based on what we noticed here, that torque is dependent on these two things. It's dependent on
Force.
and the,
Radius.
right? Does that make sense?
Yeah.
You make either one bigger, the torque gets bigger, so you're probably going to need to multiply them together. So the torque is equal to the force times the radius. Okay? Is that okay? Now there's one little piece that I haven't told you yet. And I'm gonna tell you that right now. So again, I'm gonna label this so that everybody knows that this is the door. I'm gonna give you a situation here. I want to know which one's gonna have the greatest torque. So I'm gonna have the same force. So all 4 of these have the same force. Are you with me there? Here they come. So I'm gonna apply a force like this. I'm gonna call this one FA. I'm gonna apply a force. I'm gonna call this one FB. I'm going to call, let's see, we need more colors. This one, oops, I didn't actually label that one. Sorry. FB, FC, and FD. I want you to right now to kind of think this through, figure out which of these forces will be the biggest, and then rank them from biggest to smallest. Which ones will have
Force.
no, the torque.
Okay.
So which ones will have a bigger torque? The forces are all the same magnitude.
Where's the hinge?
Right here.
Okay, I wasn't sure if that was like a rounded edge of the door.
No,
or-
that's the rounded edge of the door.
Okay.
I don't know why you guys can't interpret my art. Come on.
Looks like a doorknob.
That's, we've had this conversation. Everybody else can ask. You already know. This is the axis, okay? Go. Do this in your head first. You and your brain. All right. Take a minute to talk to your teammates. Have a conversation. What did you figure out?
I think it's FD.
Let's come back. Let's see here. Reagan, did you guys come up with an answer? You had, it looks like you were kind of having a good debate over. That's what I'm asking. Can you let us all in on what your conversation was about?
Well, we're just trying to decide, like, if we need.
They thought we were trying to see which has the biggest force, and me and Victor thought we were trying to see which has the biggest torque.
Okay. So I'll answer the question. All of the forces are the same.
Yeah, that's
So we want to know which one has the biggest torque.
Okay.
That said, did you guys come up with an answer, or do you want me to take you off the hook?
Thinking it through,
Yeah.
then FA would have the smallest torque, and wait, never mind.
No. That is correct.
Oh, it is?
Yes.
Okay.
I agree with that. Does anybody else agree with that? I probably shouldn't have said it was correct, because now everybody's like, oh yeah, I agree with that too, sure. Let's compare just A and B. How do A and B compare? Same force, right?
Same rating.
What's different, Hannah?
The FB has a bigger radius from the center.
But they're both being applied at the same place.
Bigger angle.
Do you see what I'm saying? Because otherwise, yeah, because it's like over, you did it. But yeah, if they're both being applied at exactly the same place, then the radius is the same and the force is the same. But I said I agreed with you, which makes it no sense then, huh? She's talking crazy talk, yeah.
The angle for B is
There it goes.
closer to 90 degrees, so you're hitting it straight on instead of pushing your force in a different direction.
Wasting some force,
Yeah.
right? Yeah. If you want to get something to open, you need to push it exactly perpendicular to where the door is. Does that make sense?
Yeah.
Yeah. Whereas this guy here, I mean, like this one who's pushing this way. Friends, you guys have enough experience opening doors now that you know that it doesn't make sense to apply a force this way. But, okay, I don't know if you've ever tried to watch a little kid try to open a door. It's kind of funny. Like one who just has, and not funny like, ha ha, you moron, but like funny like, you haven't had enough life experience to know. I'm serious. I would never say that.
You just did.
Now you're lying too.
I always lie to you. You know this. All right, so come back with me here. If you've ever watched a little kid try to open a door, some of them, I mean, like sometimes there's a probability that sometimes they're going to push perpendicular. That's great. But sometimes not so much. It's kind of funny. You're like, but it's a life experience, right? It's not that they're not smart, it's that they've not had that experience before. Pushing this direction, will you be able to open the door?
Eventually.
Sure. It'll just be harder, right? Yeah. Yeah. Well, even without a lot more force, you will get rotation, it just won't rotate as fast or as much, yeah. Yeah. So A is smaller than B. We're not really sure about these. It kind of depends on that angle, I guess, huh?
Yeah.
But what do you know about C as compared to D? D is bigger or C is smaller? Does that make sense to everybody? So, yeah, what's up?
Okay, so is it like when we were doing gravity on a ramp, and gravity is straight down, but we wanted to figure out what it was perpendicular to the ramp?
Mm-hmm.
Is it sort of like that with the forces, since the force isn't perpendicular?
Mm-hmm.
If you split it so it's like a square, the force
Triangle?
Triangle,
Yeah.
yeah. The force going this way,
Yeah.
it doesn't matter because that's that direction the door has to move, but the force this way does, since it's smaller than the force going this way.
Yeah.
and left.
True statement. Did you guys catch what she just said?
Yes.
That was fantastic and lovely. So I hope you caught it because I'm going to say it one more time, but it's short. So here we go. If we take FA and I break it into components, right? This is FA that's perpendicular, this part right there. Are you with me there? Is that okay?
Mm-hmm.
That's the only force that's actually doing any good. This force down here, wasted force, right? Like not doing anything to help get that door rotated. Okay. So there's a relationship in there. So as your physics teacher, I am going to encourage you to write this down as the force times the radius from the axis to the force applied, and that force needs to be what to the axis? What is it? Perpendicular, yeah. Okay? Now, in your book, when you're looking in the book, it's going to say that torque is equal to F times D times the sine of theta. So let's unpack that a little bit. The F is just our force, right? What do you think D means?
Distance.
Distance? It's not, because in the book, if you look up work, it says force times distance times the cosine. Here's the weird thing. From a fundamental, like physics, I've studied lots and lots and lots of physics, and I'm looking back on it. Torque and work have zero to do with each other, okay? There's some calculus that has to happen to make you really convinced of that. I'm not going to go through the calculus with you right now. You take AP Physics with calculus with me, and we'll go through it, and you'll be like, oh, of course, they have nothing to do with each other. But for right now, I'm just going to have to ask you to trust me, okay? They don't have anything to, they look a whole lot alike. I like to write this with R for radius because that makes more sense to me. It's not like, I mean, when we talked about talked about work, I was applying a force over a distance, right? Like that's the D. That makes sense to me. But this D is not really, it's a radius, right? It's the distance from the axis to where the force is applied. Does that distinction make sense to you? Is that okay?
Yes.
Okay. So it looks a lot similar, but it's not. It actually has nothing to do with it, which is kind of annoying, right? They look a whole lot alike, but they're not. So that's the one I want you to put in a box with stars and glitter and whatever you need to around it, highlighter and whatever. This is the one that I really want you to know. Okay. I've got some kind of thinker problems for us to look at to see if we really get this stuff. Are you ready? I like this question.
Ooh, scary.
It's not scary at all. It's great. And then I'm going to show you something also, but I want to do this problem first because I like the problem. It's kind of small, so I'm going to read it for those of you, especially those of you that are in the back, so you're not like, I can't see anything. And then I'll also make it a little bit bigger. So these lovely pictures are of signs that are suspended from equal length rods. Okay? So you're like, you know, signs like outside of business or something like that. Okay? In each case, the mass of the rod compared to the mass of the sign is small, so we don't want to worry about that. You probably weren't even thinking to worry about that anyway, so don't worry about it. If you wanted to, don't. Okay? The mass of the sign is given in the figure, so we got 50 kilograms, 100 kilograms, 50, and 90. Okay? In cases B and D, the rod is horizontal. In the other cases, the angle that the rod makes with the vertical is given. The task for you is to rank the magnitude of the torque that the signs exert about this point. Thinker question. I'm going to turn off the front set of lights so you can see a little bit better. I'm going to give you about a minute or so to think about this by yourself. I want you to write down something, okay? Try to figure this out. Do your best. I will give you a chance to talk in a minute, but I want this to be you and your brain first, okay? Give it a think.
The force of gravity, or the force for sign B is going to be greater than D.
What do you guys think? Do you agree with that?
Yeah.
Okay, so the force is going to be the same, and the radius is the same. Or excuse me, the force is different. The radius is the same. So are we okay here? Okay. And then we had some different things going on here. So either C and then A or A and then C. Go.
This is not an answer but a request. Can we call them like boards or posters or something? Because one of the two equations has sign in it, and calling them sign A, B, C, and D is getting me confused.
Yes, we certainly can. What do you want to call it?
I really don't care as long
Pick.
as it's not sign.
Pick.
Potato.
Potato. We're going to call them
No,
potatoes.
llama.
No, potato. You missed your chance, my friend. All right. So in situation A or situation C, with potatoes hanging off, they have the same mass. Do we agree?
Yeah.
So they have the same force. Do we agree?
Yeah.
And they have the same length. Do we agree?
Yeah.
So there's something that has to be different because they're not equal. Oh my goodness. Let's see if we can share the fun here. Does anybody else want to assert something? Katie, I haven't talked to you for a long time. Go.
I think it's C and then A because the part that actually does
That applies a torque?
yes, that applies a torque
Uh-huh.
is greater in C because it's the part that's perpendicular to the surface
Uh-huh.
is bigger in C than A.
Okay. Esmara, you look like you want to say something.
No, okay.
Gemma wants to say something.
Are the signs moving? Or
No.
Potatoes? Are potatoes?
No, they are all at rest.
Well, then wouldn't it be
Potatoes
zero? No.
Not necessarily because that's a really good question.
Okay.
Okay, so I want to pause everybody so that you hear that question because it's deep. That was a deep question. So Gemma said they're not moving, right? If they're not moving, then the net torque should be what? Zero. Does everybody agree with that?
Yeah.
That's a huge deal, and that is true. I want you to write that down because that's a big deal. In this case, if you want to a potato example, then you could say that the net torque equals zero in all of them, but we need to look carefully at the question. I'll fix it so that we're all okay. It says to rank the magnitude of the torque that the potato exerts, right? Not the net torque. So, Gemma, I would agree with you if it said net torque, that every single one of them would be zero.
Okay.
That's a good statement, but that's not what it asks.
Okay.
So is there, let me ask this question, because we think that the net torque is zero, we think that the potato exerts torque on the rod. So what does that mean also has to be true?
There has to be another.
There has to be another torque.
There has to be another one. Where do you think it comes from? Or do you have a question? I'm not sure which
I'm
one.
just a little bit confused.
Yeah.
G net as zero.
Torque net is zero. Why? Why is torque net zero?
Because there's no movement.
No movement, no rotation, which means there's no acceleration, which means there's no.
The total torque of all things together is zero.
Yeah.
But we're just determining what the torque is of the signs on the
Potatoes.
Like, I understand
potatoes
that.
on the
But
rods.
sorry. I understand that, but if there's a force and a radius,
There's a torque. That's true. There is. Okay, so let's say this one more time. I want to make sure everybody's listening because we got to keep going. So much to do today. It's so exciting. There is a torque acting on this stick, right? From the potato. But there's another torque acting as well. Where is it coming from?
The wall.
Right here. Do you want to say it? Say it.
The wall.
The wall, yeah. The wall is also applying a force to the stick. Okay? Does that answer your question?
Yeah.
Okay, so now I want to come back to Katie's statement. She's like, wait, what? That was like a long time ago. Let's go back and we got to go fast. So if we look at this, so if we have a force going like this is the force of gravity. Does everybody agree with that?
Yeah.
I can break that down into two pieces, one like this and one like this. And then we're going to get our mad geometry skills out and say we only care about this part right here. Are you with me there? Yeah? Let's look at our angles and see what happens. If this is 30, what's this?
30.
And this plus this have to add up to 90. So this thing here is 60. Are you with me there?
Yeah.
And we're talking about this little piece, and you all know from your triangles that the biggest angle or the bigger angle is going to be across from the bigger side. Does that sound familiar to you from geometry? I taught that to some of you, and I know the rest of you should have learned it. So this is going to be the little side because it's across from the 30 in that triangle. You can do the same thing over here. So here's the same force, but this is going to go like this and like this. So that's going to be your 30-degree angle. So that's the little side. So that's the bigger side. Did I go too fast through that, or was that okay? That was kind of a lot of triangleness happening. So this one's got to be bigger than this one because this one has a bigger force perpendicular. Is that okay? Pausing for questions. Seth, how you doing?
Good.
Are you feeling good about this? Good, okay. I just haven't heard from you today, so I just wanted to check and see. Wesley, how are you doing?
Fine.
You okay?
Yeah.
All right, Rachel, how are you doing?
Pretty okay.
Are you sure?
Yeah.
Okay. Do you want to ask any questions, or are you? Okay. Okay. Keep me posted. All right. We got to keep cruising. Here's another one. Here's another one. This one is not quite as chunky. Here it comes. You ready? I kind of feel like maybe in elementary school you had something like this, and you didn't realize that you were doing torque when you did it, but like with balance, probably not with keys, but with other things. So let me read this to you because it's a little bit fuzzy, so listen carefully. 5 identical keys are suspended from a balance, which is held horizontally as shown. 2 keys are on the left attached to the balance 6 centimeters from the pivot, and the 3 keys on the right are attached 5 centimeters from the pivot. What's going to happen when they let go? So I want you to think about it, think about it, think about it, make a prediction. And not only is it going to fall, because I don't think it's going to stay still, which way is it going to fall? That's the other thing I want you to think about. So I want you to give that a minute. Yeah, I totally should have recorded you saying that. Can you say it one more time really fast?
So 6 plus 6 equals 12, and 15 times 3 equals 15. Yeah.
I got you. Yeah.
So 15's greater, so it'll fall to the right.
Boom. Is that okay? So I think in elementary school they have these things as like multiplication practice, right? Yeah. But really you're just studying torque. They just didn't say it. I know, right? Because if you think about this, they're all perpendicular, so really it's just a force times the radius, which is really just torque, yes? Okay? This thing will rotate, which means that the net torque is definitely not zero. Okay? The next thing we need to write down, here we go. Oh my goodness, I'm so excited. The next thing we need to write down is a word that I don't think I've actually used and I intended to a long time ago. So I apologize for that. But here's the word if I haven't used it yet. You tell me. Have we said this word before?
Not in this class.
I don't know how this is possible. I don't know how I made it through all of chapter 4 without saying this word. I didn't intend to, withhold it from your vocabulary. I apologize for that. What does it mean for something to be in equilibrium? What does it mean for something to be in equilibrium? Go, Rachel. Does it have to be at rest?
No.
Can it be at rest? Yes, it can be at rest, or it could be, what would be the other way to say that? That covers everything? There's one little bit we need to talk about. Go.
Isn't when the Fnet is 0?
Yeah, that's what we've talked about for a long time, right? Equilibrium is when Fnet equals 0, and as a result, we know that the acceleration is 0.
Actually, I'm pretty sure you used this word at least once.
I just can't remember. I haven't used it as much as I had hoped. Yes.
So isn't that like when both girls were pushing on the table and it wasn't
Yes. Yes. Now, here's the deal. Go, Asmara.
Wait, doesn't the net torque also have to be 0?
Why? You are absolutely correct, but I want to know why you said this. She's like, I just... Can I help you fill in the answer?
Yeah.
Okay, let's take a look back at the picture of the table. Fnet was 0? Was this table in equilibrium?
Yeah.
Gut feeling? Absolutely it was. Fnet is 0 here, right? Is this table in equilibrium?
No.
It is not. So, in order for this thing to be in equilibrium, it needs to not be moving, but also what? I'm waiting, you're good.
Trader.
That's hard.
Jankany.
It's kind of hard, huh? It's kind of a hard question.
Raise the season.
What's what?
Isn't it like not moving constantly? Is that how you say it? I don't
Yeah,
know.
yeah. Yeah, so it's either not moving at all, or it's not accelerating, right? Is that a fair way to say it? So you can have something that's rotating, but it's not speeding up or slowing down in its rotation. That would also be in equilibrium. Is that fair? So let's put all of that together, because that's a lot of stuff. Wow, you guys are awesome. Okay, so Fnet has to be 0, and torque net has to be 0, so that it's not speeding up or slowing down its rotation.
Wait, Miss Carboy.
What's up?
If something's rotating, doesn't that mean its acceleration is not 0?
It's a good question. So here's the deal, is that one part, so like if you think about like a turntable, so, and if you don't know what a turntable is, you can just think of some sort of like flat thing. Oh wait, here. Speaking of, let's just pull it out and look at it. It's like I had it here on purpose. I didn't actually, but it works out. So here's a turntable, right? When it's spinning and spinning and spinning and spinning, there are ball bearings in there to help it make it almost frictionless, okay? And so if it was actually frictionless, it's going to keep going forever and ever and ever and ever, right? Even though there are no forces acting on it. Are you with me there?
Yeah.
So there are no forces, so no torques either, okay? So even though like this little piece of the board is accelerating, the system as a whole is not. Does that make sense?
Yeah.
It's a really important distinction, but yeah. Does that help a little bit?
Yes.
Okay. Okay. So we gotta write this down. Okay. Man, I just want to keep you guys through lunch so I can keep talking to you. Okay. So, what was I gonna say? Asmara, what did you say? What was the whole point? That it
Can't be like rotation, can't be accelerating.
it's not accelerating, so it can't be spinning up or slowing down, right? Okay. So, I told you, don't pack up yet. I've got like 2 more minutes. 2 more minutes, and I need them with you. Okay. Here's the deal. Do you remember in chapter 4 when we were looking at problems and you set Fnet equal to 0? And then you could solve for like the forces acting, like how big is the frictional force? Well, if you know this and life is good. You can do the same thing with torques. So for example, I was going to actually do an example with you. I will try to get it recorded so you can watch it on Monday. But let me give you an example here just so you have this to kind of look at later. So let's say you have an object with a little fulcrum. Like you may have, I don't know, experienced something like this in your past, right?
A seesaw.
Yeah. A balance beam, a teeter-totter, a seesaw, something like that. So here is one object. We'll call it object 1. Okay? And here is another object. We'll call it object 2. Okay? there are ways to make these two balance about this point, even though the distances are different. Are you with me there? Okay? In order for this thing to balance, the net torque must equal 0. How do you find the net torque? So it's going to be this one, so like F1 times this distance, we'll call it D1. Is that okay? F1 times D1. And the other one is F2 times D2. Are they going in the same direction? This is a tricky question.
No.
The forces look like they're going in the same direction, but would they cause the same torque? No, because that's the fulcrum, right? That's the balance point. Bless you. So in fact, one of them is negative. I'm going to tell you that this one is the negative one, and I'll put that in the video so you can watch it. But these two have to balance out so you can find a mass. Does that kind of make a little sense? Yeah. Cool. All right, my friends. So I will not see you until next Friday. It will